Hi guys, so this week you are going to be ending quantum mechanics. The end of quantum mechanics is actually talking about light, how light waves work, how color works, which is one of my favorite units all year. We had so many fun labs and I am really bummed, but hopefully you're going to get to see some cool things in the activity this week. Some of the things that they're going to talk about is like, why is the sky blue? Or is it actually blue? Or is it just a function of how our eyeballs detect light waves? And you'll get to see things like that and how your eyeballs work in the activities that we're going to do on your first assignment for light waves. So I'm just going to break some things down. If you watch this video through, it actually does give you quite a few answers from the activities that you're going to be going through in light. So it really should kind of cover your basis other than the videos it wants you to watch. So this one and then those videos and that activity would kind of be all you needed to do, probably, if we just pay attention now. So in light waves, it is a wave like that. So light comes in a wave. Light mostly for us coming from the sun, so white light. If we don't remember from grade school, white light is composed of all colors, and we'll kind of break that down in a second, but it is literally a wave that's coming out. It's like a wave of energy. So it does not matter. It doesn't have mass, but it is energy. Now, this is how we, like the vocab terms for wavelengths of how to determine it. If this is a wave, these peaks at the top, these peaks are called crests. The bottom are called troughs. So we have crests and troughs. If I measure the top of a wavelength from crest to crest or from trough to trough, that is the distance of the wavelength. So when someone says the wavelength is really small or really big, it is the distance between literally that wavelength of energy. It's top to top. So it's crest to crest or trough to trough, okay? And then we have amplitude, which is how high. So either going from the midline to the crest here, or I could go from here to here as well. That's amplitude. And then it has to tell you which direction the light is going. So that's kind of breaking down what a wavelength is. Now, how do I use wavelength? The size of the wavelength, so what we just talked about a second ago, the size from crest to crest. The size of the wavelength determines how much energy a wave has. It determines the color that we might see it as. It determines its energy, its frequency. All of that is determined by its size. So basically all we're gonna be talking about mostly in this unit is the size of the wave. The bigger the wavelength is, so the longer the wavelength, it has actually lower frequency and lower energy. So it's like less dangerous to be around it. It has like less heat, less energy all around. Whereas if the wavelengths get smaller, so shorter wavelengths have high frequency and high energy. So it's kind of like backwards thinking. You would think the bigger wave would have big energy, but it actually doesn't. The bigger the wave, the lower the energy it has. So an example of things that have really big waves is like radio waves. So like literally the radio that you turn on in your car is a wave of energy. Now it's not a wave of energy that our eyes can see. We're going to talk about visible light in a second, but it is a wave of light. It's just not a light that our eyes can detect. And it is ginormous. Some radio waves are the size of mountains. And those waves have really long wavelengths and actually have really low frequency, really low energy, do not hurt us at all. They just go right over us because they're huge. As we get to smaller spectrums, so up here, the smallest one we're going to talk about is gamma rays. We talked about gamma rays before in the nuclear unit, and I said that gamma rays were like the most powerful. And I told you the reason why they were the most powerful is actually because they're the smallest. They're tiny. They're so small, such a tiny, tiny little wave that they can fit inside your skin and actually cause cancer, cause damage to your cells because they can get inside. If it's a big wave, it can't really, it's just going to go right over you. Where the smaller it is, it can actually go inside your body and do damage. So gamma rays are the smallest. Now in between those two things, we have this like big electromagnetic spectrum of big waves that are radio, and then TV waves and microwaves, and then we get smaller and smaller like X-rays and gamma rays. Those are getting really small. In the middle of all that is the visible light spectrum, visible as in to us, our eyeballs visible. Our visible spectrum, this is missing yellow, red, orange, yellow, green, there should be like 2 versions of blue, indigo and blue and violet. I'm missing a yellow, I don't have a yellow marker. So, but basically our visible colors are the rainbow. Those are the colors that our eyes can detect. Now in that range, I've showed you already, red is the biggest. So your eyes pick up the fact that things are red around you because it's a bigger wave. The smaller it gets, it goes to orange and then yellows. And then we have our greens and our blues, and the smallest color we can see is violet, actually. So kind of how we determine these colors is actually just the size of the wave. It's not like color necessarily exists the way that we might have thought it existed. It existed as in size of wavelengths of light. Now, all these colors come from white light. And I want to show you a quick example of 2 little labs that are actually in our activity. So I'm going over it now. In the activity, it says you can research it, which you still can do. You can research more about it, but I'm going to show you it now. So it's going to talk about doing it with a prism. What am I supposed to do? Shining a light through a prism, shining white light through a prism and making a rainbow. I've tried to do it several times and like I can get it to work, but it's not bright enough to show up on tape. So like on this video that I'm making. So I'm using the CD because the CD is just, it's gonna work the same way as a prism does. It's gonna separate white light, but it's a little brighter. So I have my white light flashlight, here we go. Okay, I shine it on the CD. Why is it blinking? Whoa, there we go, regular light. And then, so I need to get, there we go. So you see that rainbow showing up. It's separating white light into the visible spectrum. So when all these colors come together, it just makes white light. But when I separate it with a prism, it's separating them by their wavelengths. So their wavelengths are kind of syncing up with each other. The big waves are the red, and the medium waves the yellow, and then the green and the blues. And the purple we can actually hardly see till I kind of move it that way. But all those different sizes of waves are linking up with each other and causing it to where I can then see the different spectrums of waves. When they all join in one big loop, it's just white. So white is a combination of all colors. The second part, the lab, this is the end of the video, is called refraction. So let me see if I can get this glimmer out of the way. Kind of. So if you're looking at it, do you see how the pen is here and then it kind of like hops over? And over here, the pen's a little harder to see, but it's like, and it kind of hops back over. So kind of it just looks like it's been cut in half and hopped over. You can see the same thing if you're swimming in a pool and your body kind of looks like it's over here and your top half is over here. Now, why is this happening? It's called refraction. So refraction is when, so light's coming in. I have sunlight in here coming in, it's hitting the water. Now it's a wavelength. It's a wavelength of light, and so light travels the speed of light. But when it hits things, it does slow down. So it's traveling at the speed of light, or almost, because there is air slowing it down a little bit. And then it hits the water. The water is much thicker than the air, much more dense. So it's going to separate the light at a bigger degree. So if I was gonna kind of try to draw what that would look like, is you'd have that light coming into the water, so it hits the water in the cup, like that, okay? So it's coming in, and then it's, as it slows down, it just kind of like bends, and you see that bend in the water because it's slowed down for a second, and it's moving what you would see just over just a little bit, just because it's slowing down what your eyes can detect from the water right there. So those will be the 2 things you'll look at as refraction, how rainbows work, how you can make white light turn into all those colors. And then, like I said, why is the sky blue? How do your eyes work? These are all cool things we can learn about light. So there we go. There you have it. There's a little recap on light. I hope y'all are having a good week.